So there are a few questions before we start. A question from Bintao is that could you give us some project templates to follow, which we can follow the project lifecycle step by step. The end-to-end project that we discussed earlier is a classical example of the project template and that you can follow. Also, could you recommend us some deep learning projects in Kaggle? So most of the projects are there at Kaggle, and we have put 3 projects in this particular course. You should take a look at them. Most of them are inspired from Kaggle or other competitive places, and you should take a look at those. All right, so let's get started. So till the last time we talked about reinforcement learning, and at reinforcement learning, what we learned was that there is an environment, there is an agent, and agent observes the environment and then takes the action. That is reinforcement learning. All right. Great. So there were many examples of reinforcement learning. One of the examples is, say, playing a game, and or even the way a robot or human walks around in an environment. That's an example of reinforcement learning. So what agent does is, as part of the reinforcement learning, what agent does is agent observes the environment and takes an action and then optimizes or maximizes the reward and so on. So this is what agent does. All right. So agent takes an action, agent takes an action, and environment gives the reward as well as gives it entire state. So based on the state and the reward, agent takes an action. So most of the time the agent's aim is to maximize the reward, but sometimes there can be no reward at all. All right, let me talk about those. So in real life applications, there are many more real life applications. These are the major ones like walking robot. But in case of, let's say, handwriting correction, so there could be an environment where let's say you are assisting there is an assisted robot which is being assisted by you to do the text correction. So those are also example of reinforcement learning. So walking robot is the classic example of reinforcement learning. And learning to optimize rewards in case of Pac-Man, for example, we are trying to play Pac-Man and we are trying to maximize the goal. So the next example is thermostat that we talked about last time. The thermostat is an interesting example because this is something that we never thought that it is based on. It could be involving deep learning. So in case of thermostat, the 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 reward is there is only punishment, and the punishment is in case the human tries to adjust it. That's a punishment for the thermostat. So and all right. So the reward as such is not there. It's the only reward it can figure out is that whenever the agent is close to the target temperature, and negative reward is when human needs to tweak the temperature. All right. So agent must learn to anticipate human needs. That's the objective of the thermostat. There could be auto trader which will trade in the stock market, and it observes the stock market prices and decides how to buy or sell every second. All right. The rewards are very straightforward in this case. These are the rewards are basically the monetary gains and losses. There are many examples such as self-driving cars, then placing ads on a web page or controlling where an image where an image classification system should focus its attention. So there are many applications which you'll find that where the reinforcement learning is used very often. Now, basically, reinforcement learning is um, a bit of strategy plus combined with whatever we have learned so far in deep learning. All right. There could be scenarios where there are no positive rewards at all. For example, in this maze, it only has punishment, and the punishment is based on how much distance the how much steps the agent has moved. Right? In this maze, let's say the agent will move around, getting negative rewards at every step. So it finds the objective of the agent is to find the exit as quickly as possible. All right. So to play to play any of such role of an actor, there are something called we there is always a policy. So the objective is to figure out a policy and then work on that policy, optimize the reward or punishment by the way of that policy. Okay. Say for example, the agent works on a policy, and based on the policy it takes action, and the policy gets a feedback based on rewards and observations. The policy can be any algorithm we can think of, and it does not even have to be deterministic. For example, consider a robotic vacuum cleaner. Its reward is the amount of dust it picks up in 30 minutes. Its policy could be to move forward with some probability every second, or randomly uh, move forward with some probability p, and every second or so randomly rotate to the left or to the right with a probability of 1.5 p, 1 minus p. And the rotation angle could be random. So this is a very simple policy where it'll just whether move ahead or rotate and move ahead and so on. So it'll keep on shifting between the two. But this could be very ineffective. All right, very ineffective sometimes, and such policies where there are a lot of randomness involved, we call them stochastic policy. This robot will have the robotic vacuum cleaner will have erratic trajectory, which guarantees that it can go to any place it can reach and pick up all the dust. The question is, how much dust will it pick up in 30 minutes? After long time, as in after fairly long time, such robot, which is completely erratic, will pick up the dust. But question is, how much time will it take? So the next question is, how would we train such a robot? All right, let me just check if we are recording. Yes, recording is going on. So in this case of robotic vacuum cleaner, there are two policy parameters which we can tweak, the probability and the angle R. The probability P is moving forward, and remaining part, the 1 minus P probability is to rotate, and at what angle. All right, so one possible learning algorithm could be Try out many different values of these parameters and pick the combination that performs best. Okay, this is an example of policy search using brute force approach. Let's say there are two parameters, P and R, and we have to, and these are the various values of P and R possible. And the brute force approach could be either this, could be like this, could be like this, and so on. This is what is brute force. Brute force is trying all permutations, either randomly or in certain sequence, in certain sequence. All right. If we are following a stochastic policy, then finding the finding the finding the most optimized value of parameters is like searching for needle in the haystack. And this could be almost impossible because just by random luck achieve we cannot achieve the optimum parameters. That's why we need to do gradient descent and other things that we have done so far. All right. The nature's way of achieving a similar thing is by the way of the way we interpret it is as genetic algorithm. So the genetic algorithm basically works on the principle that it will randomly create first generation of hundreds of policies and then trying them out, either let them get killed or kill the worst policies, and let the survivors replicate. This is basically what we refer to as genetic algorithms. In genetic algorithms, what we do is we spawn a lot of parallel permutations and then see which one has, after a while, then see which one has uh, diverged, and then we kill the one which has diverged and let the one that has survived replicate and do more. All right. So that's the genetic way of genetic algorithm way of solving it. All right. So the surviving policy plus their offspring together constitute the second generation and continue to iterate through generation this way until a good policy is found. The another good approach is to use an optimization techniques. Evaluate the gradients of the rewards. So evaluate the gradients, as in the gradients mean evaluate evaluate the rate of change of error with respect to your your parameters, and then tweaking these parameters by following the gradient, the slope, towards the highest rewards, as in the lowest error, the way we had done earlier. So this is basically what we are referring to, the gradient descent. All right, let's understand this with an example. Going back to the vacuum cleaner robot example, we can slightly increase P and evaluate whether we can slightly increase the P, as in the moving forward, the probability of moving forward, and then evaluate whether this increases the amount of dust it gathers. All right, and pick up the amount of dust getting picked up by the robot. If it does, then increase P some more, and then otherwise, if it is not happening, if increasing P has increasing P has resulted in in less dust, then we should decrease the P instantaneously. All right. So this is basically what is called a policy search. We have already done this part as part of our understanding of the gradient descent. And so I would like to walk you through the OpenAI Gym and then continue with the rest of our discussion. All right. So to train an agent in reinforcement learning, we need a working environment, right? We need a working environment where our agent can do some action, it can receive some feedback, and then learn from it, and then again take an action. So we need a working environment. So we might have to, let's say, the example that I gave in the session one of Mario, to do that, we might have to set up a NES game simulator, or let's say Atari game simulator, and that could be quite time consuming. And but luckily, there are some open source projects such as OpenAI. OpenAI has Gym, a, open source package called Gym, which is a toolkit that provides wide variety of simulations like Atari board games and 2D and 3D physical simulators and so on. So we don't have to create the simulator or hook ourselves to the simulator. We already have one provided by OpenAI. All right. So I would like to walk you through simple example. So here, what we are going to walk through is a very simple, we will try to balance the pole on the top of the moving cart. The objective of the exercise is the pole should be upright. So we have to move, let's say the pole is falling to the left, we have to try to move to the left so that pole remains straight and so on. So this is the objective. This is the environment in which our agent is supposed to play and perform the actions such that the reward is maximized. The reward here is time, time or number of steps for which the the pole was balanced on the top of cart. All right, let me try to show you. Okay. All right, those who have not pulled their repository, they could go to cdml. All right. CD deep learning, and you could say git pull. Has everybody pulled the repository? No? Great. Now moving ahead into the deep learning folder. In here, you will see reinforcement learning. All right. So this is a common setup function in which we have reset graph as well as saving figure, updating scene. These kind of these functions are required for the animation part. You will notice. All right. So we're going to walk through the cart pull example. So first of all, we need to import Gym. Then we need to create the environment. It's basically the 2D simulation in which we have to balance the cart. So we have just created the environment called env. Its name is this. Okay. So this one, all right. So each observation the cart will give us, that the environment will give us, will be the cart's horizontal position, its velocity, its velocity. Where did it go? Yeah. So cart's horizontal position, cart's velocity, the angle of the pole, as well as how fast the pole is falling. Okay, so in either case, whether the cart goes out of the view or the pole goes beyond an angle which is balanceable, in both the cases, in both the cases, we lose. Okay, so here we are saying environment.reset. So this is the observation we got. The initial observation is what we get initially. So if we run it, we will see that the initially these are the parameters. This is the position of the cart horizontal. The second one is the velocity of the cart, and third one is the angle of the pole, and fourth one is the velocity at which the angular velocity at which the pole is falling. Okay, so all right. If you want to render to return the rendered image as NumPy array, you can set the mode to RGB array. All right. So to make it run, if there was a UI and GUI, we could have run it easily from the desktop. So we are going to add these extra functions, which basically render the image. Okay, so that we can display it here. So now you can see that this is our card. All right, this is our card, and this is the pole. At that point of time when we took this snapshot, okay. So the other thing that environment gives us the action space, how many actions are there? Discrete 2 means there are possibly two actions that we can take. The integer 0 and 1, which represent 0 means move to the left and 1 means move to the right. So the step function provides us the method to move the cart to the left or to the right. And it provides us the observation. Okay. It provides us the observation. Now, if the cart is moving to the right, the first observation, that is the speed of the cart, is going to be 0. The pole is still tilted. Okay, let me go up. Okay, so to the right, if the third value, okay, I'll actually show you this part. Yeah, this one. All right. Okay. So here, the here it shows that it's a new observation. If the first value, this one, is greater than 0, that means the cart is moving to the right. The pole is tilted towards the right if this value was positive. But in this case, since it is negative, that means it is tilted towards the left. The angular velocity is now negative. Okay, now negative. This is angular velocity. So it's going to be all right. So it's going likely to be tilted towards more left. So the angular velocity is also towards the left, as in negative, which is the anti-clockwise, and this angle is also to the left. Therefore, chances are it's going to fall to the left. All right. So all right. The it will finish. So here, when we say step, when we say environment.step, it returns us 4 values. Okay. First one is the observation that we discussed just now. Second one is the reward. Second one is the reward. In this game, you get 1 point every time at every step. Okay. And done will be true if the game is over. And this info is extra. This info is something that provides an extra information for debugging and so on. All right. So here we'll just run through one example without. We are just moving to the left continuously. We are taking. We are moving to the left. All right. So question from Bintao is that are there names for the results of obs? Which command get these names? There should be a name. All right. Okay. There should be something that would give you the name. Yeah, I think this is the one. All right. There would be some names, but from the documentation, the observation, the various values are essentially these. Okay. So you can say OpenAI Gym. All right. It should be there in the documentation. Essentially, for now, we can just make a note, and these are the various observations, as well as we have uh, talked about it earlier. Okay, the velocity, the angle, and then angular velocity. Those are the four values. Okay, so here, let's say if I run the environment from beginning and keep on just moving to the left, taking the step to the left, then this is what will happen. Now, after a while, when it reaches a certain angle, it stops and says done, because there's no way to recover from it. There's no way to recover from it. Okay. So here it is returning when we say, give me one more step. It is returning true. Here, if you run it again, it returns true because it is already done. All right. So that's about it. So when the game is over, when the pole tilts too much, not when it actually falls. Now, when we were moving to the left, the pole was tilted to the right. Now, when we have moved to the right, pole is tilted to the left. All right. So though we are able to make it move around, make it move around, but it's going to take a bit more strategy to balance it for longer. Okay, to balance it for longer. Now let's just if we can count how many steps we moved. Okay, so let's say steps equals 0, and here at every step we are just increasing the total number of steps, and then once we are done, print the steps. Okay, that's what we wanted to print. So we took total number of 9 steps. We took total number of 9 steps. This time we took around 10 steps. A question from Kamal is, can we not see the movement process in action and not just the final state? We can see. I'll show you. We can see that process also. All right. So okay, let me just show you this part. So the easiest one, I'll just replicate this part. Okay, let's just replicate our easiest policy. And here what we're going to do is, at every step we are going to maintain an array of frames in which we will append the images, and once everything is done, then we will render it. We will plot the animation, and we will. So we're just moving to the right. So that's all. Okay. So if you want to give it a shot, this is basically a simple strategy. We could say 0 to the left. Okay. We could say 0 to the left. Okay. So that way. It just it stops very quickly. Okay. So also we could do a little bit of right. So I should have moved to. So if we divide it by 2, okay. So yes. Wow. This time it went to 43 steps. Okay. It's pretty simple one. All right. A simple strategy here, what I. All right. So this is the animation they give, and I'm not sure how you can make it slower. You can just see the environment if they give you the documentation. All right. So here I did a very simple tweak in this strategy. First, what we were doing is here at the top, we were moving to the left alone, and then we were moving to the right. So we were getting around 9 to 10 steps. But this time, what I did was first we moved to the left, then to the right, then to the left, then to the right, and that's what we did. So here I'm getting around 56 steps. Okay, so you could give it a shot. And this is how it looks like. All right. So now these were the three policies that we have designed so far. The first policy was just keep moving to the left. Second one is try to move to the right. The third one is for take a step left, take a step right, and keep on doing that. Okay. Okay. Now that was now we could create another fourth strategy in which if the pole is tilting to the left, then push the cart to the left and vice versa. Let's see if that works. So here is a case where we are starting with environment reset, render cart pole, adding the image to the frames, and then taking all the observations, all four of those. So you notice that when we are resetting the environment, we're getting the initial state. And then when we take a step, then again we get the steps and we instantaneously get the state. So here is the simple policy whereby if the angle is less than 0, take left action. 0 means left. And otherwise, take the action as 1. All right. So here, let's take a look at it. So you can see it was able to move to certain number of steps. We could also count the number of steps. Okay. So let's say a number of steps equals 0. And let's just count it every time we take a step. And then we print number of steps. Okay. So this strategy is better than the previous one. Previous one was taking us to 50 or so, but this one is okay. But this time it did not work that well. So these are the two strategy we have come up with so far. So first strategy is to uh, first strategy was that was working well is move to the left, move to the right. That's all, without any observation. The second one is taking observation into account, and if it is tilted to the left, move to the left. Otherwise, to the right. All right. Do you think that if we apply machine learning in it, we will be able to achieve more than these steps? No. All right. So next step is that we can create a neural network that could play, that could basically observe the outcome and take action accordingly. All right. So we're going to discuss that part. So far we created very simple policies. The first one was only related to just moving left, other was only moving right, third was one left, one right, fourth one was based on the angle of the pole. So here is a neural network policy that we would be creating. So what we will do is we'll take observations that will go into our neural network, and then we will create the another layer, the output neuron will be basically a sigmoid function. Output neuron will be a sigmoid function and will basically give 0 or 1. It'll give the probability of action left. Okay, that means remaining probability, if the probability is zero point 0.5, that means it's 50-50 left. If the probability is 0.1, that means zero point 0.1 for left and zero point 0.9 for right, and so on. So it'll basically give the probability of going to the left. So it's going to give us one decimal number, which is probability with which it should go to the left. Okay. Now, in this game, what we are doing is after it has predicted the probabilities of all the actions, instead of just picking the action which is maximum score, okay, we are using something called probability, multinomial sampling. Okay, let me repeat what I said. So here it's going to give you the probabilities of various action. Okay, based on the environment, it's going to give us, it is going to give us the probabilities of all actions. Here, since there are only two actions, we are just getting one probability, that is for moving left, because remaining probability is for moving right. Okay, so this neural network is going to give us suggestions whether to move left or move right. And those suggestions are based on the strategy or the policy that we'll come up with. Okay, now these probabilities, instead of just taking the action which is the max probable, we do a little bit more smarter thing here, which we call multinomial sampling. Now in this, what we do is we pick the, instead of picking the action with the highest score, we just pick a random action. We pick a random action based on the probability given by the neural network. Now, what does it mean? So I'm going to just show you this simple example, and then you'll get an idea. Okay, so we are going to use this function called multinomial. Okay, so here, let's just take a look here. We are importing TensorFlow, although not required because we already have this. Then we are defining, say, probabilities of three actions, 0.1, 0.1, and 0.8. These are the probabilities of three actions. Now we're going to use the multinomial function. Okay, so this one is going to give us, let's say there are three actions, 0, 1, and 2. So multinomial is going to give us the random action, and that randomness is not purely random, it is slightly biased. The outcome should have 80% of the time 2, 10% of the time 1, and 10% of the time 1. Okay, let's just take a look if that is the case. Okay, let me just import TensorFlow. Import TensorFlow as TF. Okay. So here you can see, I'll just separate it out. Okay. So you can see that this has given us around 80% time, around 80% time, 1, 10% time 1, 10% time 0. This is 10% time, and 80% time 2. Okay. So this is what it means. Does it make sense? Because I know that it could be a little tricky to get it. Let's say there are possibly two outcomes. Okay, we are tossing a coin. It could be head or tail, 0 or 1. So in that case, if you want equal, then we say 0.5, 0.5. That means give me the probability, give me 0 and 1 both with equal probability. Okay. So, and then we call the multinomial with tf.log of p and so on. So this and we are asking that do the 10 times, do the coin toss 10 times. Okay. So it is almost like equal probabilities. All right. Okay. So if we, let's say, increase the one, let's say there are two states, 0 and 1. This is 0 is states for head, this is state for tail. If we increase that to say 9 and decrease it to 0.1, then this is 0th index, this is first index. So we are saying the 0th value will be really rare while 1 will be more frequent. Okay. And in the same way, if we, let's say, increase that one to 0.8, so you can see mostly 0. Okay, this time. All right. So it's basically giving the random selection based on the probabilities. Okay, based on the probabilities. Is it making sense to you? Okay, so instead of just choosing, let's say we got the probability of 0 as this much. Let's say our neural network is suggesting that, hey, take the probability of taking 0, action equals 0 as is 0.8, and the other one is 0.2. So if our neural network is suggesting this, so ideally, if we just take maximum, we should just take the first action. First action could be left, and this is right. So we'll just take left. All right. That's what we will. That's what we usually do. But we are asking the random number generator. Okay. Again, we are doing a coin toss here. Coin toss such that coin toss with a coin which is this much biased. Okay, this much biased. That's what we are doing. A question from Bintao is, what will happen if the sum of p is larger than 1? Good. It doesn't give an error, but ideally it wouldn't make much sense. So I'm not sure why it is not giving error, but it's kind of mistake, and maybe it is normalizing internally. Maybe it's normalizing internally. All right. Is everybody clear about the function of multinomial? No? Balaji, Bintao, Gigi, James, Kamal, Shahrukh, and Pavan. All right. Now, question to all of you is, why are we doing so? Why are we not just picking one action? And why are we doing the coin toss again? Why are we basically picking the random action? Any answers? Why are we picking a random action based on the probabilities given by the neural network instead of just picking the action with the highest score? Anybody? It's a very important part. So our neural network, as we are going to design it, our neural network is going to give us the probabilities, right? It's going to give us the probabilities of whether to take left or right. Now, instead of just taking left, if the probability of left is higher than the right, then instead of doing that, what we are doing is we are doing again a coin toss, okay, such that based on the probabilities. Okay, based on the probabilities. Why are we doing that? Anyone? So if let's say the probability the neural network gave us zero point 0.6 and zero point 0.4. So instead of just taking left, we are doing the coin toss in this way. So it might give us 1 also. It might ask us to go to 1. A question from Kamal is here observations are for this run or past many such runs? The past run actually. So we have imagine that we have trained the neural network and it's working perfectly fine. We got the outcome. We got the outcome, and the outcome says 60% chance of going to the left, 40% chance of going to the right. So what will you do? Will you just go to the left? All right. Or let me rephrase my sentence. My sentence is that neural network is suggesting that you should go to the left, and the recommendation is 60% recommended going to the left and 40% recommended to go for going to the right. Okay. Question is, will you just go to the left or what will you do? That's right. So based on the last state, based on the current state, our neural network is suggesting that, hey, you shouldn't go to the left, 60% chance of go to the left, and 40% would be suggestion for going to the right. These recommendations will keep on changing. So given a state of the environment, the neural network has suggested us that 60% chance of going to the left and 40% chance is going to the right at a particular state. Now, will you just go to the left or will you again do the coin toss? Okay, all right. So you can just ignore this one, okay? Because the example was designed for something else. All right, am I making sense to you? So question is, let's say there is a neural network. There's a neural network. We fed the whole environment, all of the parameters that environment gave us. And then we got the probability of the outcomes. And here, instead of just taking action, we are doing the sampling again. We are again doing the coin toss, kind of coin toss here. But coin toss is little biased on the same lines as this probability. Why are we doing that? So the inputs to the neural network are going to be the observations of the environment, right? Okay. So here, let me just show you this. So every time we make a step in the environment, when we say like move the let's say x1 represents position of the card, x2 represents the x2 represents the whether the cart is moving to the left at what speed, or x3 represents the x1 represents position of the cart, x1 represents the velocity of the cart, x3 represents the angular velocity of the pole, and x4 represents the x3 represents the angle, and this one is angular velocity. This one is position, this is velocity, this is angle of the pole, and this is angular velocity of the pole. That this is the input to the neural network. So we asked the game that, hey, can you give me the current state? Game gave us these 4 observations. We fed those 4 observations to our neural network that we have already trained. And this neural network is giving us the probability of taking various actions, whether to go to the left or right. All right. Was I able to make it clear? Let me just share the slides again. All right. Now, question is, what we are saying that after we feed our neural network the current state of our game, and the neural network has suggested the probabilities of various actions. That hey, uh, in my opinion, the neural network is suggesting that, in my opinion, take the 60% chances of going to the left will benefit you, while the probability of right one should be around 40% because it doesn't look like too probable, and so on. So that's the probabilities that neural network is going to give us. Now, instead of you just taking its suggestion, you again do eeny, miny, miny, mo at this point, and then take some action. Okay, you do multinomial sampling. Just that instead of purely random, you do the coin toss with the same kind of bias as the outcome of the neural network had. Okay, so question is, why do we do that? Anybody? So why we are picking a random action based on probability given by the neural network rather than just picking the action with the maximum probability or maximum score? That's right. Introducing some randomness, some experimenting. That's correct. So we basically giving the serendipity a chance, and that's what it means. So this approach lets the agent find the right balance between exploring new actions and exploiting actions that are known to work. Okay? All right? It's like we going to the restaurant, and every day, instead of just having the dish which have known to prove really well in past, we are giving a try to the new dish. Okay? So it's basically a way of discovering new things. Essentially, in simple words, it's giving serendipity a chance, not like doing serendipity all the time, but we are giving serendipity a chance. Okay, so it's not like we are ignoring the entire learning of the past, just that from time to time we are trying something new. That's why that multinomial sampling is done. Okay, question from Binta is, what is the highest score here? Okay, what is the highest score here? Which one we're talking about? Okay, highest score will be like here, the zero point 0.6. Let's say our neural network gave us these probabilities. Neural network gave us these probability, zero point 0.6 and zero point 0.4. Okay, highest score is action going to the left. Okay, neural network is suggesting that zero point 0.6 is the action to go to the left, zero point 0.4 is for going to the right. Okay, that's what it means. Okay, the score here is going to reflect upon the points that you gain. Okay, and here the score here is for each action predicted by neural network, that hey, this is the chance of taking this action. That is the score we are talking about. All right, did I make sense, Avinta? All right. So basically, this is what we are doing, and okay. Now let's move on to the actual code. All right. So let's reset the graph. Now, here we are going to create our neural network. All right. Is everybody with me on this? So here we are saying that number of inputs is 4. Okay. Number of inputs is 4. Why? Because there are 4 observations that are coming from the environment. And since it's a simple task, we are saying that the the hidden layers are only 4 and outputs are 1. Okay. Since we are only predicting the probability of going to the left. Okay, because remaining probability indicates the indicates the probability of going to the right. So the outcome of the neural network is the prediction whether to go left or right. So therefore, there is only one output neuron. Then we are creating an initializer based on variance scaling initializer. All right. A question from Mintao is that what does the what does this part means? It's essentially a function for initializing and is based on statistical way of initializing values. Okay, just like batch initialization we did. Should take a look at this one. Should just put it here, put a question mark, press command enter. Returns an initializer that generates TensorFlow without scaling variance. Okay, so it essentially generates the random numbers which are scaled instead of too high or too low. Okay, that's what it means. All right, should we move ahead? Great, great. All right, so for initializing the weights of these hidden neurons, we are basically using this initializer. Now, in this example, it's a vanilla multi-layer perceptron with a single output. Okay, basically the single output is going to use the sigmoid and the logistic function. If there were more than two possible actions, we would be having one output neuron per action. Okay, so now once we have defined our initial variables, then we are creating the hidden layer. Hidden layer is basically taking X as the input. X is our placeholder. That is the data we are going to inject from outside. And these are the hidden neurons, the number of neurons in the hidden layer. And this is the activation function, and this is the kernel initializer for this hidden layer. Then we are creating the output layer with number 1 neuron, and the input is the hidden layer, and the activation is the sigmoid. Okay, and the kernel initializer is the same initializer. Now this is our outputs. Now we call first, this output is going to be only one number, correct? Therefore, we are concatenating the right and left to it. So it gave us 0.6 or zero point 0.4 to go the probability of going to the left or going to the yeah, it will give us the probability of going to the left. So we are computing the probability of going to the right. So that's the probability, which is 1 minus this value. Okay, we are concatenating the two. This is the outcome. Now we are using the multinomial function to give us the next action. We are asking the multinomial function that based on these probabilities, give us the next action to move, considering the randomness. All right. So let's get started. So we have defined this. Now we are defining these x and y, then multinomial. Okay. So in this particular environment, the past actions and observations can safely be ignored since each observation contains the environment's full state. If there were some hidden state that you may need to consider past actions, then that will be different. Okay. A question from Binta is, what is the function doing here? This one. This is basically concatenating these two. Okay. So if you take a look at the outputs, it's going to look like this. So outputs is something like, let's say 0.4. Okay. So what we are doing is we are concatenating, let's say 0.4 and 0.6, right? One minus point. This is right. So we have to concatenate these two. So this function that you see here, this concatenate is going to basically convert this into something like 0.4 and 0.6. That's all. All right. This is what is happening here. So if I have to, put it here in the comments, this is what is going on. So 4 is getting converted into something like this, and then these are two getting merged. All right. Moving ahead. So, all right. Now let's take a action ahead. You can go through whatever we have written in the comment. All right. So what we are doing here is we are not doing any optimization as such in the first sort. What we are doing is doing the environment reset in the beginning. Okay, that will give us some observations. So on one hand, we'll have the neural network. On other hand, we'll have the game. The two things that we have to talk to. All right. So right now we are just talking to the environment, which is the game, and then we are rendering we are appending the frame here, and here we are evaluating the response of the action. Okay, what was the action? Action was nothing but the predictions. So based on the initial values of weights, whatever it predicts, we are going to just take that. All right, we're just going to take that. All right. So a question from Binta is, why do we have axis as 1? Because we are going to merge this and this. If we were used axis at 0, the answer at this point of time could have been little different. It would look like this. If we were merging on axis 0, then the answer would look like this. I'll show you. Okay. It'll look like basically something like this. Okay. Do you see the difference between this and this. Okay. And all right, great. Moving ahead. So yeah. So what I was describing is all we are doing right now, we're not doing any, we are not utilizing or optimizing any neural network. Whatever random values we have generated so far, whatever random values we generate so far, we will just evaluate, compute the action and see what it is giving. So it's basically the random action, not nothing much. Okay. So a question from Binta is that it does concatenate, but around the first axis. Okay. There are this is two-dimensional values, correct? It has x and the y, right? And if it has two dimensions, right? Okay, it has two dimensions. So we basically concatenating it such that it is basically, it comes as single row rather than two rows and one column. All right, that's what it is. So instead of concatenating columns, we concatenating the columns, we could have concatenated only the rows if we use axis equals 0. All right, notice that each of the value is a two-dimensional value. All right, great. So at this point, we are basically not doing much. We are essentially just asking the neural network, but neural network is still not trained. It is only full of random values, and those weights are basically random weights generated by the function. They don't have any knowledge about our data. Therefore, it wouldn't really be useful. Okay, it wouldn't really be useful. Okay, that's it. It is worse than our previous example. All right. Now let's try to code it, and then all right. Now let's try to improve upon what we have done so far, and then let's see if we can. All right. Let me just see. Okay. All right. So now we again basically improving upon the same example. So we have defined x. X is our input. Y is our expected output. And there is a hidden layer. Then there is one more layer for logits. And then we have outputs, which are basically this is basically the output layer if you combine these two. And we are computing the probability after doing multinomial. And then next thing is we are comparing the the logits with the labels, and then computing the cross entropy. And then we're defining the optimizer, Adam optimizer with this learning rate, and then this is our training operation. And once we have done that, we define the initializer. Okay. So logics is just nothing but a logistic layer, okay, which is the outcome of our dense layer of neural network. Okay, it's a next layer of neurons, which is to which the outcome of our hidden layer is fed. Yeah, we're just giving it a name. That's all. Okay. Now we are now here we are creating 10 parallel environments. Here we are creating 10 parallel environments, and we are observing all 10 of those. Okay. So we can make the same net play in 10 different environments in parallel and train for 1,000 iterations. We also reset environments once they are done. Okay. So what we're going to do is, so we are, okay. So what we are doing here is we are starting iteration. Here we have created the environments. These environments are equal to these environments, and we are iterating over, say, total possible iterations, which is 1,000. And okay, so here underscore is just to ignore a particular value. Okay, ignore the iteration variables. You could put any other variable as well, but this is explicitly to mark that we are not going to use this particular value. That's the use of underscore. Okay, now here what we are doing is we are saying if observation 2, which is the angle of the pole, if it is lesser than 0, move to the left, otherwise move to the right. That's what we are doing for each of the observations in this iteration. So here we are calling the reset on every environment, and similarly for each of the observations, this is what we are doing. Okay, and we are making it run for a while. Again, um, here, here you can see this is the target, the probabilities. We are basically feeding this target as here and optimizing the learning. Okay, so this target probability, the predicted one, is based on very simple thing, which is not right. Okay, so it's based on very simple thing, and since we really don't know the outcome, we really don't know which action is better than other action. We'll know only in future that a certain action was wrong. Okay, therefore we are right now using this mechanism, as in we are just training it using this particular logic. We are training it with this particular logic that if it is tilted to the left, go left. If it is tilted to the right, go right. Okay, that's how we are doing. All right. Training up is not defined. Oh, we have not defined it here. Okay, so that's what we have done. And then we are doing the rendering of it. Okay. So it is little better. Training operation is here. Training optimization operation. Training up is defined here. Okay. This is optimizer dot minimize, and then we're passing the cross entropy to it. Okay. So it is doing a little better. It is doing a little better than what we have done in past. Okay. That's it. So it is doing really good as compared to our previous experiences. Uh, All right, we could just see if we have steps equals 0. Let's see how many steps are there. Okay, and then here we print steps. So how many steps were there? I think some 40 steps were there. Yeah, 43. Okay, so this time lesser. All right. Still, it's not good enough. It's a very simple mechanism we have used. We've trained it using our knowledge that if this is tilted to the left, move to the left. Okay, but that's not good enough. Let's discuss the policy gradients. Okay. All right. So now there are a couple of problems at this. One is that we don't know that how do we basically train our network. Okay, our network is going to give us an action whether to go left or whether to go right. Okay, and how do we know that this is a correct action? We will only know it in future that a particular action was right or wrong. Okay, or okay, so we could, if we knew the action to take, we could have just trained it usually, and by just minimizing the cross entropy between the estimated probability and the target probability. That could have been just straight uh, answer. Okay, or even if, let's say, human is playing and we are observing the steps, then also we could have trained our our game based on the human's actions. Okay, so but here when we have an environment, we know we know our current score, but we do not know which action would be right, actually right, and we can compare the predicted right with the actual right, and and then optimize our weights accordingly. Okay, so that could have been just simple supervised learning. However, in reinforcement learning, the only guidance the agent gets is through the rewards. And rewards are pretty sparse and delayed. Okay. For example, if the agent manages to balance the pole for 100 steps, how can it know which of the 100 actions it has taken in past were good and which of them were bad? All it knows is the pole fell after the last action. But surely, this last action is not really responsible for the whole fall. Okay, so this is where the credit assignment problem starts. When the agent gets the reward, it's hard for it to know which actions resulted or which actions should get credited or blamed for it. Think of a dog that gets rewarded hours after it behaved well. Okay, dog will not know that for which actions the dog is being rewarded. That's why if you see during the training of a dog, what they do is they give them instant reward. Okay, so that the dog does not have the credit assignment problems. Okay, so I mean whatever we have learned in this course actually has taught us a lot about the animal brain and the general behavior. So this is one of the ideas. So even with the animal training, the credit assignment problem does exist. Therefore, there we basically give the instant feedback as much as possible. Okay. The same is true with our case that we don't know why a particular action. If we just start blaming that the last action was wrong, then that could be wrong. That may not result in appropriate neural network. Okay. So to tackle this problem, a common strategy is to evaluate an action based on sum of all the rewards that have come after it, usually applying a discount rate R at each step. Okay. So generally we discount the previous action's credit about 5%, which is like we carry over only 99%. So what we do is we evaluate the overall outcome of action later on in the future. Okay. So imagine that we have taken the action right, and we are saying the discount rate is 0.8. So at this point of time, when we took right, we got a reward of plus 10. Then another right, we got a reward of 0. Then another right, we got a reward of minus 5. Now in this, when we got punishment of 50, does it mean that only this much is responsible, this one is responsible, or only this action is responsible? Okay. Ideally, all of these are responsible. So what we do is here we basically out of so minus 50 out of minus 50, this one will get the blame of minus 50. This action will get the blame of minus 50. This one will get the blame of 80% of it, which is minus 40. This one will get the blame of 10 plus minus 10 plus 0 into r plus minus 50 into r square, which is minus 22. Okay. So the reward is calculated in future after a couple of steps into the games. Okay. This is how this is called the policy gradients. These are called the policy gradients. Okay. These are called the policy gradients. Is everybody clear about what we're talking about? Okay. So is everybody clear about this, the way what's happening here? So we take an action, say we took a right action, we got a reward of plus 2. Again, we took another right. At this time, instead of getting plus 10, we got 0. Now, this action alone is not responsible. Instead, the previous action was also responsible. Then we took after this, we took another right. This time, we got minus 50. So this action, the last action, is not alone responsible. Therefore, the blame goes or the credit goes to the previous one also. Okay. So these are called basically these are credit assignment problem. And to tackle this, we use the strategies of policy gradients. So PG algorithms, policy gradient algorithms, optimize the parameters of policy by following the gradients towards the higher rewards. One of the popular class of PG algorithms is called reinforce algorithms. It was introduced in 1929 by Ronald Williams. Here is one common variant. So the algorithm by Williams is the one which is being used. It is not in 1929. It must be reinforced by Ronald Williams. Okay. Reinforce Ronald Williams. That's R square, Binta. Is it 92? Oh, it's 92, not 29. Okay, that's what I was wondering. It cannot be. All right. All right. So here's a common variant of reinforcement learning. Let the neural network policy play the game for several times. Compute the gradient that will make the chosen action even more likely. Okay. So the way this is the important part. So it says that compute the gradient such that the chosen action is more likely, meaning whatever action we are taking should be the one that the network predicts. And do not apply the gradients yet. So the first one is let it play the game sometime for some time. Do not try to optimize right now. And then once you have run it for several episodes, compute each action's score. Whatever action we took, we compute the score of it, that one. And then based on these scores, now we go back and then we do the gradient optimization. Okay, if an action's score is positive, it means that the action was good and you want to apply the gradients computed earlier to make the action even more likely to be chosen in future. However, if the score is negative, it means the action was bad and you want to apply the opposite gradients to make this action slightly less likely in the future. The solution is simple to multiply each gradient factor by corresponding actions score. All right. So, and finally, once all of this has done, so once we have computed the gradients of all the stages, then we compute the mean of the resulting gradient factor and use it to perform gradient descent step. Let's take a look at the code. A question from Bintali is that why r squared to minus 50? So I'll just go back and I think that will make more sense to you. Yeah, here. So minus 50, when credit goes back to this one, so minus 50 into 0.8 plus 0, right? That is 40. Now, when the credit goes back here, plus 10 plus minus 40 into 0.8, which is 32 plus minus 32 plus 10, which is minus 22. Okay, 0.8 into 40, that is 32 minus 32, and then plus 10, this is minus 22. Okay. All right, so let's take a look at this one. This is going to be an interesting exercise. So till here, everything is normal. So we are importing TensorFlow, we are resetting the graph, we are defining total number of inputs as 4. One hidden layer has 4 neurons and number of outputs are 1. This is clear. Learning rate, as usual, we are going with 0.01. And initializer, this is our function that would initialize each of the weights. This is the input placeholder, and then we have a dense layer. Then we have a dense layer with the activation function and the kernel initializer. Now, this one is again the second layer with only one neuron. It's going to be okay. This is a dense layer which takes the hidden input as the input and total number of output, that is 1. And then we are doing sigmoid on top of this to convert that into probabilities. And then we are concatenating the action with concatenating the probability of going left with probability of going to right. And then using these probabilities, we randomly pick one action. Okay, in the same with the same chances as the probability. Okay, now since we are acting as though the action that we chose is the best possible action, the target probability must be 1 if the chosen action is left. Okay, so here is basically in the beginning just to generate data or just to take the initial steps. This is what algorithm says. Do whatever you did last. Okay, do whatever, consider whatever action you have taken is right. Okay, consider whatever action you took is right. All right, though it's completely random, but we are just taking that as right. So this is what it does. Whatever action we took, if action is 0, that means we want to go to left, otherwise we want to go to right. That's what this action means. Okay, next is we defining the cross entropy, that is a usual cross entropy with here. Then we have the optimizer, Adam optimizer, and afterwards we are computing gradient. This is the important part. So instead of just optimizing this time, because what we generally do is we say optimizer.optimize, but here we are computing gradients. Okay, we are computing gradients. Computing gradients, it gives us all the optimizable variables along with their values, along with their gradients. So that's what is the compute gradient does. Now we are extracting all the gradients here into an array. We are ignoring the variable names of each one. Yeah. Okay, a question from Bintali is, what is Adam optimizer? Adam optimizer, remember, adaptive modified, what was it, adaptive, and there was one more term. So it essentially was the fastest amongst all the optimizer in the gradient descent, right? So when we are talking about deep learning training models, there we talked about the fastest one, which basically accelerate really fast, okay, which has adaptive momentum optimizer. All right, in which it accounts for momentum as well as it is adaptive. So that's what is Adam. We are extracting all the gradients, the rate of change of each of the weights, and rate of change of errors each as per the weights. And then what we are doing is we are computing after extracting all the gradients. Okay, we are later on, we are creating placeholders for the gradients rather than just computing and applying the gradients. What we are going to do is we are going to compute the average. We are going to basically do the credit assignment because we don't want to give the punishment to the algorithm right away. Instead, we're going to give the right, we're going to take the gradients, compute the average, and give the credits in the same way, the way we just defined. Therefore, instead of algorithm letting it penalize usually, we are going to change that. We are going to compute the average gradients and then do the credit assignment and then give the value back. This way, the gradients which each of the weights receive would include the proper credits. Okay, so that's what we are doing here. We are basically creating placeholder for every gradient so that we can inject the value later, and we are appending the gradient placeholder to all of this, and afterwards we are here in the last, we are we are applying the gradients. Okay, so right. So what we usually do is Adam optimizer, we initialize with the learning rate, that's the constructor. And then on this optimizer, we call a method called optimize and we pass the loss function. But this time, instead of doing that, we are computing only the gradients. so that we are giving a chance to our algorithm to extract the gradients, do the credit assignment, and inject it back so that it can apply the gradients again. Okay. So here at this point of time, it computed the gradient, and then it is giving a chance for somebody to inject it from outside because we have created placeholders here. Okay. That's what we have done here. All right. Now, once we have computed all the gradients, now what we are doing is we are computing the discounted rewards. There are two functions which we have created. One is discounted, other is discount and normalization. Discounted is exactly like the way we defined. Okay. Discount is just like the way we defined. So we go from right hand side. Okay. We reverse how did we do this one, right? So we started here, we started here, right? And then we kept on multiplying with R, then add to the value, then multiply with R, add to the value, and so on. That's what we did. And that's what we are doing here. So whatever rewards we get, okay, whatever rewards we get here, we are going to use this function to convert that into discounted rewards. So we are going to reverse it, and we are going to start from the left after reversing. So there we are saying rewards at that step added with discounted rate of the previous one. And then whatever is the outcome, we put it in the cumulative. So initially the cumulative is 0, and then rewards at the step 0 plus 0 multiplied with the discount rate. That means the cumulative reward will equal to this one, correct? In the initial one, okay? At this stage, the cumulative and the actual one is the same. Then we go to the next step, and then there is rewards step at 1. This one called 0. And then we multiply the cumulative rewards, whatever was the previous one, which was minus 50, into discount rate, which is 0.8. Okay, so that's our cumulative rewards, and that's how we keep going back and back. After we have computed the discount rate, we would like to normalize it, and this is what's happening here. So what we are doing is we are going over all the rewards, compute the discounted rate, and once we have done that, then we are, right? This was two-dimensional, so we have converted into one-dimensional here by doing NP concatenate. And then we are reducing it. We're converting that into a single value. This reduced mean. And then we are also computing the standard deviation of these flattened rewards. And afterwards we are computing the normal value, right? How do you compute the normal value? Normal value is computed by subtracting any value by the mean and dividing by the standard deviation. That's what we have done here. So first of all, we discounted the rewards by going back, and then we have computed once we have computed the discounted rewards, okay, keeping the credit assignment problems in mind. Then we computed how far each value is from the mean by with respect to each standard deviation. So remember the p-value, or what was the term that we used? So how many times each value, how many standard deviation is each value from the mean? That's what we are computing here. All right. So once that is done, here is an example how the discount rate can be called. So say for example, in our case, we have a discounted rate of 0.8 and 10, 0, and 50, right? 10, 0, and minus 50. So discount rate of 50.8 here would give us, this will remain as such. Here the credit becomes minus 40 to the second action, and the third action will get minus 22. Okay. And this step is basically computing the standard deviation. Now, once we are done with that, this is where we are running the PZ gradient algorithm. This is where we are running the PZ gradient algorithm. We are starting from here. We are initiating the environment. Then we are saying how many number of games per update. And so what we are doing is we are going to at every step. What we're going to do is we are letting it play the game for some time by itself, assuming each action is right, and then compute the discounted rate, and then do the optimization. That's what we're going to do here. So for each iteration, we are going to go with so many games, and I mean the number of games per update that we have configured above. And what we're doing is at each step, what we are going to run the action, okay, and we are going to just feed the value of x, which is the observation, and at every step, and we are going to extract the gradients from here. Okay, we are extracting the gradients from here, and then the reward, what we are getting at every step, we are appending the reward. We are basically letting it play for some time, letting it play for these many steps. Okay, and then extracting the rewards and gradients from here. And once this is done, then what we do is we normalize the rewards. We not discount and normalize the rewards, okay, at this point. All right. Once we have discounted and normalized the rewards, then what we do is then we do the normal work here. So once we have normalized, then we compute the mean of all the values of gradients, and then we do the session.run. Then we do the session.run, and here we feed the values which are the mean. Okay, that's all right. So this way we would be able to let me just go up. I think we missed a couple of steps. Okay, did we miss a couple of steps? You must feed a value for placeholder 1 for the data type. Okay, so let me just increase the number of iterations to 150. All right, this is working fine. Did I make a mistake here? All right, I'll again start from here. Okay, so it is basically training it. So let me restate it. So what we are actually doing is, first of all, we are letting it play the game for some time. Okay, letting it play the game for some time. And once it has done playing the game, what we do is we gather the results. We gather the results, and these results basically the way we gather the results is we are also gathering the reward at every step, and then we are basically attributing the rewards backwards to all the steps, and then to the neural network we are feeding those gradients, and then we are letting it optimize. Okay, that's what we are doing here. So this is basically the gradient reinforced algorithm for policy gradients. Okay. Okay. A question from Kamal is, what is the reward here? Okay. What is the reward? You can see this is the reward here. And in the poll, mm, if you look, go up, let's go up. Okay. The reward here is basically total number of steps you have successfully completed so far. Okay. Let's just see what is the reward. What is the second variable that we get? Okay, so here I think this is where we were mentioning the right here. Okay, so here we talked about in this environment you get a reward of 1 at every step no matter what you do. So the goal is keep running as long as possible. Okay, take a look at say here, take a look at the reward. Okay, so every time you get a reward of 1. So every step is giving you the rewards. All right. So it is training somewhere down. Okay. All right. It has done the iteration of 49. All right. So you can see that it's not that bad after all. It did work to some extent. All right. So that was about the reinforcement learning. Okay. So that was about the reinforcement learning. So all right. So this time, after we applied the PG gradient algorithm, the sorry policy gradient algorithm called reinforce. It's a variant of reinforce that we have used, and it did work well. We could actually count how many steps did it get. Okay. So also try experimenting by increasing number of iterations from 50 to probably 200 or say 150, and then see how many, for how long it's able to balance the pole. Okay, so now if you want to go ahead and want to learn more about it, you may want to learn about Markov decision process. Okay, that again helps us in doing the policy gradients better. Then you may want to take a look at the temporal difference learning and Q learning. Q learning is nothing but using deep learning for the reinforcement by having many layers. Okay. Next one is you could try deep reinforcement learning in the Pac-Man. Okay. So you can take a look at this code, which is basically an extension of what we have done today. Here, basically the detailed TensorFlow way of solving, making it play the Pac-Man. All right. All right, you can see the animation. So you could take a look at that. All right. So now the next thing I want to discuss, the last thing I want to discuss is the checklist. Those who are, you can say connect. Okay. All right. Let me just give you the link. All right. So that's pretty much about our course. And in the end, I would like to just like you to take a look at a graph that I created. You could take a look at this file using any of these applications. Okay. Okay. Let's take a look if it's able to open. Oh, it's not letting me open. Otherwise, I'll have to download it and use FreeMind on it. Those who have not used FreeMind, they can try FreeMind. FreeMind is open source, simple. All right. So this is how it looks like. Okay, so how do I? Anyway, I'm just going to walk you through my diagram here. So you can also install FreeMind if you like, or you can open that's called mind map I've just shared with you. It's a hierarchical way of making notes. Okay. Okay. So here we are. All right. So this is a machine learning project checklist, and let me just zoom it out a bit. Okay. So basically, this is the one that we talked about in the beginning. So frame the problem, get the data, explore the data, prepare the data to better expose the underlying data pattern, then explore many different models, and then fine tune your model, present the solution, launch, monitor, and maintain your system. These are the project checklist. You could go into each one of them. You could go into each one of them. Frame the problem as in define the objective, how will your solution be used, and so on. Go through these checklists. We have already discussed all of this in detail earlier. Okay, and I have also put down here. All right, so that is another thing I wanted to discuss. Great. So what we've learned today is we've learned about reinforcement learning, and we've also given you the checklist of the machine learning project. And I would like to just w- give you overview of how do the projects look like. All right, so we could just click on deep learning. All right, so here the first project is classifying the clothes. Okay, so using CNN or multiple layer of CNN, you can you can basically do the fashion amnest. Okay, this is something that you can do very easily because all the dimensions that you see here are same as our amnest example. So try to achieve accuracy of more than 90% in this problem, just like the way we achieved the accuracy of 90 to 98% in case of amnest. Try achieving the same in this case. All right. Now, that is one assignment. The second assignment is distinguishing between cat and non-cat. All right. Okay. And the third assignment is classifying larger image. Okay. Classifying larger image. So take a look at these problems. If you are stuck, let us know. We would guide you as well as we will keep on updating and adding more and more guidelines to it. We don't want to add the guidelines right now. We would like you to work on these three projects. Yes, CNN for the first project, but you can try even RNN and you will notice that it is good. And the second one is, yeah, second one is the standard classification one. All right. Also try to code whatever we did today, try to code it by yourself and you will get the idea. Okay. Korean's point is they don't have access. It still says enroll. This I'll take a look. Okay, I'll just message my team. Okay, so don't worry about that. Okay, Gigi, I'll do that, get it fixed. All right, so let me just message them directly. All right, so Which ones are you not able to access? These projects only. All right, I have messaged them, messaged my team. They'll be fixing it soon. All right. So thank you, everyone. Thank you, everyone. It was great session, great course. A question from Binta is the Inception V3 model. So we had talked about Inception earlier in one of the examples. Just take a look at that one and you will get the idea. Okay. All right. Take a look at this gist. Okay. So it's basically on the same lines as what we have done earlier when we talked about Inception and other image comparisons. Okay. All right. So thank you, everyone. A question from Binta is, will you offer IoT and blockchain late? Yes, actually, the reason I have come to Singapore is to meet the IoT Singapore people. So they want to do the IoT courses for us, and I'm trying to collaborate with them. So we'll keep you updated. That is going to happen within a month. Okay. So the people who are running the IoT in Singapore, they want to basically work with us on the courses. So I'll keep all of you updated. This is going to happen in a month's time. And the blockchain is, yes, there are few other people who have come to us who wants to deliver their blockchain sessions. I would keep you updated. Most likely what we're going to do is we are going to have at least first session free from all, and then you can take a call. All right? So that we're going to ensure. So all right, thank you everyone, and you can unmute yourself and then thank you, James. I'm happy that you found it interesting. It was very good learning. Sure, Binta, we will send you a notice about whenever we are launching the course because uh, we inform our students, our all the learners first about anything, and we'll keep you updated. All right. So thank you, everyone. I look forward to see more contribution from you on the forum, as well as I look forward to see more um, feedback on Sequora or other places. Feel free to refer your friends. And right, so we have another session starting from tomorrow. And a question is, any plans to start DevOps? Would love to do it because a lot of people have been asking, but I have not actually thought about much it yet. So we were more focused on the deep learning and AI, but may plan in the future. Yes. If there is somebody who really is good at DevOps and wants to do the course, then you can plan. All right. So as per me, I most likely, if the next course I have to plan, The next course might be on security, as in me personally, not CloudxLab. So that we would anyway launch for free most likely. But the blockchain, IoT, and DevOps is something we may plan. Yes, you can attend the new sessions free. All right. Great, great. So we generally offer 1+1 free sessions, as in if you missed one course, you can attend the next course or next batches. All right. But there is no hard and fast rule as such. Okay. So great to have all of you in the session. Thank you, Balaji. Thank you, Bintao. Thank you, Gigi. Thank you, James. Thank you, Shahrukh. Thank you, Pawan and Prateek. All right. So stay connected. Stay connected. A lot of things are coming on CloudxLab, and keep your friends in the loop if they are interested in the AI and deep learning, machine learning. Okay. So you can unmute yourself and we can say goodbye. But stay connected on the LinkedIn. On the LinkedIn as well as used to be on our Facebook. A question from Pawan: do you have any open position for part-time internship? We can figure that out. We can figure that out. Can you could just drop me an email at reaches@cloudxlab. Okay. Okay. Along with the CV. All right. So that's pretty much. If you want, you can unmute and. Okay. All right. So that's pretty much. Sure. Binta's point is that my friends prefer more case study with hands-on experience. So I guess our course was more of case studies and hands-on because everything was based on one example and we did all hands-on together. Did you not? Okay. More projects. More projects are coming on your way. Okay. So the project that we generally choose during the learning part are the ones that basically cover the entire learning. Like for example, we have chosen cover the entire learning and as well as they're simpler to understand. The second kind of projects are the ones that which require a bit more work on your side. So those projects are going to be published on CloudxLab very soon for you. All right. You're going to make sure that those projects are there. Great, great. So thank you, everyone. That's pretty much. If you have anything to say, you can unmute and say. All right, great. Bye, Prateek. Bye, Pawan. Bye, Kamal. Bye, Gigi. Bye, Bintao and Balaji.
Thanks a
Okay,
lot.
go ahead. Thank you, Balaji. Okay, go ahead, please. Okay. All right, then. Yeah. Go ahead, Balaji. You want to say something?
No, Sandeep, I'll be in touch with you. Thank you. I'll meet you later.
Okay, great. Thank you, Balaji. Anybody else? Okay. Bye-bye. Have a great day. So that's pretty much for today. We are starting another session tomorrow. And regarding new session, Balaji, just drop us an email. Sorry, Binta, drop us an email that you would be interested in sitting in the new batch also. Then they will add you in that group. Okay. All right. Yes, Pratik, you wanted to say something?
Yeah, thank you, Sandeep sir, for the course. I'm looking forward to more such courses on CloudxLab.
Great, great. Thank you, Pratik. I too love to see you in more sessions. And yeah, all right. Bintao and Kamal, you want to say something? All right. No worries. So I'm going
Yeah,
to, okay, go ahead.
yeah, Kamal. Yeah. So it's wonderful. Learned a lot of things, and I think we'll have to slightly revise a few things because I missed a lot of classes in between. So I will be in touch
Okay.
with you and catch up and be
All right.
in connection with all of you all. It was pleasure learning.
Great, 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 Kamal. Thank you for a very good feedback. So, all right. Okay. Have a great day. I look forward to see you in future, and stay connected on the LinkedIn. Okay. Bye bye. Have a good day.